In life-of-field simulations, the mass and energy balances for produced fluids through a production network is calculated. The calculations commence at well inflow and terminates at the inlet to processing facilities. The networks are solved subject to user-defined production targets and constraints. The model supports multiple types of unit operations like valves, pumping, compression and separation, as well as mass sources and multipliers. Targets and constraints can be modified during the course of simulation to realistically model life-of-field responses. We support online interfacing to reservoir simulation processes, as well as proxy models to provide complete system responses. The application has a demonstrated capability, from use with fields having as many as 500 production wells. To enable life-of-field simulations, specific input data must be provided. This includes parameterizations for items or components used in unit operations, flow trajectories for wells and flow lines, fluid properties, and network incidences. Finally, the input must include references to run files for any reservoir models, as well as events which are used for well openings and setting of system targets and constraints. In order to perform unit operation calculations, parameterizations for the different items must be provided. These parameterizations are located centrally in a single file and are referred to by user-defined names. As an example, the parameterization for a pump includes a user-defined name, a maximum nominal power, and a scalar efficiency value. The pump description can be extended further to include a maximum pressure ratio, a minimum suction pressure and a maximum delivery pressure. With a known pump performance, tabulated data for how efficiency or delivered head varies with flow, and optionally rotational speed, can be included. With tabulated pump performance data, the maximum power and nominal efficiency are ignored. The branch file holds information about the flow trajectory for a given well or flow line. It further includes variations along the flow path for parameters like ambient temperature, diameter, roughness, and overall heat transfer coefficients. Optionally, it may include thermal parameterization descriptions for pipe walls. The branch file also includes definitions of locations for items and sensors for wells and flow lines. Any such item or sensor refer to the item specification file by the name of the parameterization to use. Multipliers for tuning or calibration purposes are contained in this file, as well as reference to files containing predefined fluid property data. Branch trajectory data can be entered manually or imported from files in predefined formats. Fluid data may be provided in two different formats. One option is the form of black oil parameters, where key data at surface and downhole conditions are provided. The second option is by Olga format property files, where required parameters are provided as functions of pressure and temperature. Olga format property tables can be exported from commercial PVT simulators like PVT Sim. The purpose of the network file is to describe how different wells and flow lines are connected in a production or service network. For each branch defined in the network, reference must be made to a branch file describing required data. Draw a network configuration by connecting wells to junctions and terminals. Connect parameterization files for wells and flow lines to the network. When solving a network in a life-of-field simulation, the system needs to know which items or components it can use to achieve a solution. The fastest way to define which items to use for this purpose is simply to check the option automatically use all active items in controllers. Optionally, each item to use can be defined to individual controllers. For more advanced applications, such items can be defined to controllers including PID parameters. The network file further includes settings for which pressure loss and hold-up models to use. In typical applications, a 3-phase no-slip model will be used for wells, while a slip or combined slip and stratified model are used for flow lines. The network incidence defined can be changed during runtime through events rerouting wells and flow lines to destinations differing from the original one. The network file can also be used to set default fluid properties for the branches defined. The run file for a life of field simulation includes reference to required input data, like paths for different file types, the network and item specification file to use. To enable the simulation, one or more data sources must be specified. These provide well boundary conditions in the form of downhole pressure and phase fractions used during the course of calculations. The data sources can be either a database containing predefined records for each well, or it can be a combination of proxy and real reservoir simulation processes. To include real reservoir processes, simply specify the corresponding run file. The required processes will be spawned and controlled by the life of field simulator. To realistically model life of field responses, define events to be executed during runtime. Typical examples of events include well opening sequences, initial production targets and constraints, as well as optimization mode. All of these and many more options can be changed during the course of a simulation. Just specify a condition combined with actions to execute when the condition is met. It is possible to include service networks in the calculation scheme. To do this, specify the network file representing the service network and create a map file, defining the interface points between the service network and production network. Any such interfacing networks defined will be solved simultaneously with the production network, with mass and energy balance result data stored in a dedicated database. Having completed the run file, everything is ready for performing a life of field simulation. When running a life of field simulation, the system will execute the events as defined in the setup file. Plot and see the simulation results as it is calculated. Here we see the oil rate in blue, and the potential oil rate without considering production constraints in red. The water rate is plotted in green. The water cut dominates the oil rate in the tail of the production. The calculation speed makes it an everyday engineering tool, providing quantification of technical and economic benefits. Start various calculations for arbitrary wells and flow lines during network life of field simulation. Effect of gas lift at varying rates. The branch profile shows variation in key parameters along the flow trajectory. At any time, start a cool-down simulation for any branch in the network. The initial conditions are now dictated by the current operating conditions, predicting temperature development in case of a shutdown. See how long time you have before the temperature reaches hydrate formation temperature. Control fields with autopilot production. Run forward steady state and transient prediction simulations from daily production scenarios, based on real-time sensor data. Allow true integrated field operation and optimization performed remotely from field location, with one single application.